We finished up the last video by thinking about the electric current that was being generated when we pushed a bar down a pair of rails. I pointed out there that it wasn't practical to use that for energy generation because you would have to have the rails basically be infinitely long, and that just isn't feasible. So how do we make it feasible? One way we can make this feasible is to put in a wire loop, and in practice you often have a whole bunch of windings. So again, we're going to be looking at our wire loop edge on like so. So I'll go ahead and label it. So we have a wire loop that we're looking at edge on here. And you can think of, again, like a card, like looking at an index card or something like that. The wires would be wound around the perimeter of the card. Then you're basically looking at this whole assembly edge on. Now, if, say, we have somebody turn a crank, or we go ahead and have Homer Simpson run his nuclear power plant to boil a bunch of water, to spin a turbine to turn the coil or whatever, as it's passing through a magnetic field. So this could be like a yoke-style magnet that comes around on the back side and leaves a gap in the middle. But there are a zillion different designs out there. As this goes around, this bit here and this bit here, the in and out bits, are going to be having emotional EMF generated. They'll start shoving a current along. So the way I've got this drawn here, we would be flowing a current into this. Actually, let's use a different color there. If we think about hypothetical positive charge carriers moving in a sort of generally upward-ish vibe, point your index finger along this way, turn it so that your field fingers are going to the right. You'll see that your thumb points in, which means that conventional current would flow into the screen over here. And by the same token, it would flow out of the screen over here as it's going around and around and around in the coil. Now what you do is, instead of it being just a completely pure coil, you will go ahead and attach a pair of wires. The coil had to start from somewhere and end from somewhere. So if you take the leads of the coil and you run them off, if you're really clever when you do this, you can connect these things to contraptions called slip rings. And once again, sorry for atrocious art that's about to happen. Oops. Yeah, maybe we can draw a slip ring. There we go. There's one slip ring. And then over here, oops, would be the other slip ring, like so. And these are basically free to spin around as these leads are spinning around while this whole thing is spinning around. And these slip rings would come in contact with devices called brushes, which they don't usually look that brush-like, but I'm assuming there was a historic reason for the name. So as these slip rings spin around, they slide against the brush. So electrical contact is made while this is spinning around, but it keeps the wires from getting tangled up. And then what ends up happening is we just go ahead and complete our circuit through whatever load. We can maybe go stick a toaster here or something like that, and that will finish the load. Current will flow through it and complete the circuit. Now, if we think about this, as we go through a half a turn, at first this wire was moving in general, this bit of armature here, this bit of coil here was moving in a generally upwardish way. As it turns on the top and goes down, that's going to reverse the direction of current through this bit. So this means that actually the current is going to keep sloshing back and forth through the load as we keep reversing which leg of the coil is going in which direction. So because the current keeps reversing direction, this is known as alternating current, and that is what AC stands for. Everything we've been looking to date is what's called DC, or direct current, when the charges only flow in one direction. Typical household wiring in most of the world is AC. There are a few random exceptions here and there, but it's mostly AC. And we will be getting into that later as we explore AC circuitry. All right, now, actually, before I completely turn away from this, something to think about is as this coil is turning, let's pick maybe a different color here to help clarify this. As this coil is turning, say when it's right here, the number of magnetic field lines passing through it is different than when I say here. And certainly here, when it was like this, there were no magnetic field lines passing through it at all. So the number of magnetic field lines is changing. And this should be going through the coil. And this should kind of harken back to Faraday's experiment. Remember when we energized the primary coil, what we had was a varying magnetic field, and that wound up inducing an electric field that shoved the charges around in the other coil. It seems reasonable, and in fact is correct, that we should maybe be able to extend that formulation to say even for a situation like this, where the reason why the number of field lines going through the coil is changing is because the coil itself is churning. It still seems reasonable that maybe we can extend that observation that Faraday had, and this would be correct. So on the first step to that, we are going to go ahead and define magnetic flux. So magnetic flux is our attempt to count the number of magnetic field lines that are going through a loop. FLUX. So let's go ahead and imagine that we've got some uniform magnetic field. I'll just go ahead and run it left to right across the screen like so. And we're going to look edge on at our loop. So this is my loop of wire here, and we're looking at it edge on. Now, sort of like what we do in optics, when you've got a flat surface and you need to measure an angle, physicists have this habit of measuring the angle with respect to the normal to the surface, and this is no exception here. So we'll go ahead and drop a normal like so, and then we'll say that the angle that the normal to the loop and the magnetic field make here is 0 degrees. And we can see that we have a lot of magnetic field lines going through the loop. As we let our loop rotate, let's say we go ahead and let it be out to 45 degrees or so. we'll have fewer magnetic field lines passing through it. And again, the way we'll measure the angle is we erect a perpendicular to the loop, and we say, hey, this is making, if I look right here, that's making a 45-degree angle. And then we can see that no magnetic field lines would pass through the loop if it were like this. Now here I go ahead and I erect a normal, like so. We can see that that is making a 90-degree angle with respect to the magnetic field. And we'll define the magnetic flux, or more precisely, its absolute value, to be the product of the magnetic fields, of the magnetic field strength. So the symbol is a capital Greek phi sub b. So again, here, if we have the special paper that we were all using in 3rd grade, you basically draw a capital I, and then you put a circle through it like that. Anyway, the magnetic flux is going to be defined to be the magnetic field strength times the area times the cosine of the angle. Now, and again, it's the angle of this normal to the loop that with respect to the magnetic field line itself. There is an ambiguity of sign with this definition, and there is a way to work your way out of that sign ambiguity, but generally we're not going to need to worry about that here. So we can generally think of it, for our purposes, we can just work in magnitude, because we're going to be usually more interested just in how this quantity is increasing or decreasing. And we'll work out directions, which is what the signs would tell us, a different way. Anyway, the unit of magnetic flux, there is an actual official symbol for it. It is the Weber, which is really Weber, a German name. A lot of people just write Tesla meter squared, which is what it is, but that is the unit for magnetic flux. And the whole idea is, we go and take a look. If I make the area bigger, more lines go through. If I make the magnetic field strength bigger, more lines go through. If I have the normal more perfectly aligned with the external magnetic field, more lines go through. So this is definitely proportional to the number of magnetic field lines, and in fact, this is exactly what we need. All right, so now that we've defined flux, we've got to figure out how to get directions of induced current. So we can do it like we were doing before at the generator, by thinking about all the magnetic forces on everything, and that with motional EMF. But there are cases where we won't want to do it that way. And so this leads us to Lenz's law. This is a bit of a precursor to Faraday's law of induction, and certainly a necessary part of it. And unfortunately, to be careful about this all, the official definition that I'm going to have to give you is going to be a mouthful, and there's really not a whole heck of a lot I can do about that. I'll try to break it down bit by bit. But I find that if I try to say it in anything less than about 2 or 3 sentences, long sentences, I'll leave something out. So usually the way that we'll state, Lenz's law is there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current. Is such that the induced magnetic field opposes the change in the flux. And that is the official, fully legal statement of it. Now notice I've underlined opposes the change. So it's what isn't going to be driving thinking about the way currents flow in our loop isn't going to be how many magnetic field lines we have going through it. It's going to be how the number of magnetic field lines is changing with time. And there are three ways that we can change the magnetic flux. The first way is we can just plain change the strength of the magnetic field. So if the magnetic field strength through the loop changes, the flux will change. Remember, we said that the flux is magnetic field strength times the area times the cosine of the angle that the normal to the loop makes with respect to the magnetic field. So if we increase the magnetic field strength, then we'll have more magnetic field lines going through the loop. That would mean that our magnetic flux goes up. By the same token, if we decrease our magnetic field strength, we'll have fewer lines going through the loop. That means our magnetic flux is going down, is decreasing. But there are other ways. One is that the loop can change in area or angle. So in this case here, if it's changing in angle, we already saw looking at the generator example, that if the normal is aligned with the magnetic field, that's going to be the maximum number of magnetic field lines that can pass through. And as we rotate and the normal changes its angle, we'll have a lesser number of magnetic field lines. Or if you're rotating to get the normal more aligned with the field, then the flux would be going up. You can also change the area of the loop. That might not seem quite so obvious, but for instance, what you can imagine is having some sort of an articulated contraption. So say something like, here we go. So you get some sort of hinged polygon kind of thing, and this is probably not going to work out too well. Yeah, let's say I've got something, a hinged structure that looks sort of like this. So I'm just marking where all the hinges are with dots. So I got these this is all made of conducting material. I got these segments here. Now what I can imagine doing is just pushing in on these bits here so that it becomes to look something more star-shaped. Like that. Well, in that case, the area decreased. And since the area decreased, then that would mean that the number of magnetic field lines that could pass through that area would also decrease. We can also have it that we move the loop into or out of a magnetic field, a region with magnetic field. So if I move the loop from where there was no field to where there is a field, the flux goes up. If I move the loop from where there is a field to where there isn't a field, the flux goes down. All right, so again, all of this legalistic statement here, it is a mouthful. But what I find that I can hang my hat on and to help me through this is that what I'd like to think is that if the magnetic flux through the loop is changing, what I like to think is that when you induce a current, the current is going to flow in such a direction that you are creating a magnetic field through the loop that will try but fail to keep the number of magnetic field lines through the loop a constant. So if the magnetic flux is decreasing, you'll induce a magnetic field through the loop in the same direction as the magnetic flux. Now the flux is going to keep decreasing, but it's like the loop is valiantly trying to keep that from happening. And by the same token, if the number of field lines is increasing, then you'll induce a field that points in the opposite direction, trying to cancel out the increase in the magnetic field lines. And in that case too, it won't ultimately be a successful attempt, but that is a way to think about it. Let's try to do a couple examples of this, and I'm really sorry about how the 3D drawing is probably going to go for us. So let's imagine that I have a bar magnet here. We'll make this the south end, we'll make this the north end here. And let me define a plane here. Like so. And then I'm going to stick a loop of wire in this plane. So if we go and take a look at the magnetic field lines that are coming out of the magnet here, coming out of the North Pole, we're going to see like a magnetic field line that does, oops, we're not going behind that part of the loop there. Say does this, and then maybe does this, and then maybe does this, and then similarly over here. Okay, and then of course the field lines are looping back in up here because it's a dipole, and in fact we're running within the magnet. All right, so now let's go ahead and move that bar magnet downward. So I'm just going to indicate it like that. So if I move this downward, so I'll just draw like this to indicate that we moved it downward. What does that do to the density to the number of magnetic field lines that are going through the loop here? Pause the video and get back with me. Okay, so what it's going to do is it's going to increase the number of lines. And how is that? Well, I didn't draw all the lines. Some of these lines here before missed the loop altogether on their way back to looping in up over here. If I bring this down, now this line that I drew right here will actually now pass into the loop, as will all the lines that did before. So what we see here is that the magnetic flux in this situation is increasing. All right. So what does this mean? Well, this means that the coil wants to try to keep the status quo with the number of magnetic field lines going through it. It will not succeed, but it's going to try. And so what it's going to do is the current through the loop is going to move in such a way that, let's see, let's do purple here, that the loop itself is going to generate a magnetic field pointing up. Here, we'll just label it over here. So we'll call this the induced magnetic field. I'll try to make it a little more blatant to see. There we go. It's going to try and induce a magnetic field pointing up. So if you remember from the video when we took a look at the electron that was moving around in a magnetic field, I showed you that with a loop of wire, you could find the direction of the magnetic field that got produced by the current if you took the thumb of your right hand and laid it along the loop in the direction current was flowing. The way your fingers would curl inside the loop would point in the direction of the magnetic field. So here we need this to point up. And here is where I'm going to be attempting to draw a hand, and we will probably all have deep regrets about the experience. I'm sorry. So what I'm imagining doing here is with your right hand, we're placing your thumb. We're just trying to find a direction here. It turns out I'll be guessing correctly here. But we're trying to draw in thumb like this. And what's going to happen is your fingers are going to be curling out of the curling out and sort of pointing up-ish. Okay, I tried. I'm sorry. So here, since I had the fingers of the right hand pointing up, this means I guessed correctly about which way the induced current must be flowing. So that means that the induced current is flowing around like this. So if we were to look down from above on this, we would be seeing the current flowing counterclockwise. And this is indeed consistent with what Faraday observed. If the number of magnetic field lines in some region is increasing, we induced electric field lines that were circular in orientation and circular in shape and oriented counterclockwise. So sure enough, we are inducing a current here. Now we can also do this by thinking about motional EMF. We can shift to a reference frame where we imagine the magnet isn't moving, but the coil is moving towards it. In that case there, you should be able to convince yourself that the magnetic forces would be shoving the charge around. So there's some sort of an equivalency here that we need to flesh out. Okay, similarly, if you were to move the bar magnet away from the loop, you would induce a current in the opposite direction. This is because then, if you're moving away, the number of field lines going through the loop is decreasing. You would need the induced field from the loop to point down, which means that that induced current would have to be going clockwise when viewed from above. So just to maybe make this a little more concrete, let's do one more example here where the coil is doing the moving. So I don't want my bar magnet this big. There we go. That's good. North, south. All right. So in this region here, let's This is going to look like a dipole. Something like that. So if we, again, here, let me draw a plane just to help us with the visualization here. Let's go ahead and have a loop oriented in the plane. So around about here, the flux through the loop is roughly 0. Lines are either just grazing the loop or they're coming in and they're going out. But as we move the loop, say from there to here, now some of the lines from here are going through the loop and have to exit the loop before they can come back around. So this means that we are seeing an increasing magnetic flux pointing up. So this means that we need to have an induced field that points down, which means when looking from above, we need the current to be flowing around clockwise. Now, when you're right at very dead center, here the number of field lines going through would be an inflection point. So say we draw this again right here. The number of field lines is inflection points at a max. And so at this point, the current is 0. Then when I go over here, the number of lines is decreasing. So now we want to induce an upward pointing magnetic field to try to offset that. Oops, there it is. There we go. There we go. Be induced. And so here, the induced current would be flowing counterclockwise when viewed from above. And then eventually, as we go away here, the magnetic flux tapers down to nothing. So we'll see a current increase to some max just before we get to the center point, drop to 0, then start flowing in the opposite direction, getting to the center, getting to a max somewhere a little off center, and then decreasing as we pull away. Now, this stuff takes a bit of practice here. So I've often recommended that when you're learning Lenz's law, it's not bad to just plain make a little crutch. So here is my crutch for Lenz's law. And all I'm recommending you do is you get yourself an index card or something like that and just make the following 4 diagrams. Here we will have magnetic field going in, and then we will also here have magnetic field going in. Here it will be coming out. There. And so then here we'll write that the magnetic flux is increasing, so the density of lines is going up in this row, and in this row we will consider magnetic flux decreasing. And let's just go ahead and segment this off. And so then when we think about our loops here, here where the flux is increasing going into the page, the induced field would point out of the page. And if we play around with the hitchhiker rule, we will realize that that means we have to induce a counterclockwise current. And similarly here, if we have an outward pointing flux and it is increasing, that means the induced field would have to point into the screen. And again, playing with the hitchhiker rule, we work out that this means that the induced current has to be clockwise. If the flux is decreasing, that means that we want to induce a field pointing into the screen in order to try to keep the number of lines the same. So again, that's inducing a clockwise current. And then finally here, we're going to want to induce a magnetic field that points out of the screen to keep the number of lines the same. That's going to induce a counterclockwise current. So I recommend you do, while you practice using Lenz's law, is you literally draw this diagram on a 3x5 card and use it to check your work. You can ask yourself, which situation is this most like? Am I having an increasing number of lines and it's going in? It'll look like this. It's a decreasing number of lines and it's going out, it would look like this, and so forth, until you can comfortably argue it for yourself, thinking about which way the induced field will point and use the hitchhiker rule. All right, now I did point out that we should be able to argue this if the direction of the loop is changing. So this gets us back to our AC generator. So here, exactly as drawn, as the loop is churning, the number of lines that will pass through the loop is increasing, pointed to the right. This means that we're going to want to create an induced magnetic field that points down and to the left. So let's just note that there. Like so. And again, by playing with the hitchhiker rule, you should convince yourself that that means at the top of the coil, the current is going into the screen, and at the bottom of the coil, it's going out of the screen to make that happen. Alrighty, and then finally, as we look at this, we should see if we have consistency with what we've done before with motional EMF. So if you remember the problem we did in the previous video where we had the 100 ohm resistor here and we had rails a meter apart and we were moving a conducting bar down like so, and we had our magnetic field going into the screen. We had worked out from the right-hand rule that this would give us a counterclockwise current. Well, now a different way we can visualize this is to say, okay, at some time later, this bar is going to be over here. This will have increased the area of the loop. By increasing the area of the loop, we've increased the number of magnetic field lines that go through the loop. So this means we will want to create an induced magnetic field that points out of the loop, like so. And again, by using the hitchhiker rule, we can work out that that is going to give us a induced current that is going around counterclockwise, just like we saw before when we did this with motional EMF arguments. And it'll turn out that it'll always be the case that if there's more than one way to do this, we jolly well better get the same answer either way. Physics has to be internally consistent. And it actually, with a lot of careful work, you can prove that these two seemingly different looking approaches, motional EMF versus Lenz's law, for instance, are actually the same thing under the hood. It isn't particularly obvious, but it is. Alrighty. So in the next video, we will get into Faraday's law of induction proper and end with a fun little demonstration. Catch you over there.